I write a compiler for my own programming language called Elna. It is a small, simple, Oberon-inspired imperative programming language, and I do array access and array access expressions. I already wrote a function that converts the abstract syntax tree for an array access expression into the 3-address code. It's still not complete, but it is enough to do the first steps. So just this small procedure. It converts the array index to 3-address code first. Then it multiplies this index by 4. So we assume in the first test that the size of each element is 4 bytes. We save the result in this LHS variable. It begins with a dollar because it is a pseudo variable, or pseudo register. Then we calculate the expression for the array itself, and we add this index of set to the address of the array variable, and it's our result that we return. So I already have a type which I use for the tests, and this type is this R1 record. It has 3 fields, and the second field is a 3-element static array of words. And to do some testing, we will modify this record. Not modify, but add a different record that has the same memory layout, but doesn't use array. Then we can check that the memory at specific spots has the right values. We probably could just do it with pointers, but well, we'll define another record. So we need here a few more fields. We call them field 4, 5, and 6. And this record is then twenty bytes long, the same as R1. So we can now update the 19th stage of the compiler that we use for testing, and the record definition is here. And let us assign something to a field. So we can do then field 2. 1 is 3. And field 2 is 5, for example. We can remove this line for now. And let us first read the values that we get from the array So we just use this printf statement and add another parameter, and we print first this r fill to 1, and then the same with the second element. So where can we see the result? So we print a comment into the output, and we need the build validation stage 19th, and CL assembly. And we have 3 and 5 values here. So at least these data are saved at some offset and then retrieved from this offset. And then let us introduce an R2 variable, and we will assign this R variable to R2. There is no proper type checking yet, therefore such assignment works. In the final version of the language, it should be of course fixed, but we are not so far yet. I think that, so we need R2 here, and fill 2 by 1 was filled 4, I think, and this one was filled 5, and it doesn't work. Of course, it should be the other way around. And then we read the assembly, and it is 0 and 3. So what was the layout? 4, 5, 6. Okay, 4, 5, and 6. And now we have the correct values. So this works so far, but there are still few things that should be fixed. The first one being that our arrays won't be zero based as in many other languages, but the first element of the array will have the index 1 and not 0. So we will need an additional instruction here. And probably we can update the index instruction. So the instructions are a list, and here we append the offset instruction to this index instruction list. It shouldn't break anything, I think. And when we just copy this add instruction and subtract, we replace it with subtract, and our target register is this LHS. But it is the add instruction. So our second register remains the same as here, so it is what is returned by this binary expression, because the index is binary. Is a binary expression, or binary expression is the most general expression in the current implementation. And the second operand would be just be an immediate value. So this one is actually the second operand, and we need the third one, and it would be an immediate value of 1. The length is 0 then, because the length is meaningful only for strings. After we do that, we can multiply this value now by 4. But the value isn't in this operand value anymore, but it is in this LHS register. So we can remove this thing and say that this is the second operand. Then what we have to do, we need to append this add. No, actually the other way around. We can actually just say that instruction is just a word. So we use this concatenate function, and we say that in the instruction list concatenate, and then we merge these two instructions, add instruction and the offset instruction. And here, instead of appending the offset instruction, we append the add instruction, because it is the first one in the list. And that is actually it. Now we have to update our test code in the 19th stage, but we want probably to copy this function so that we can test with it again. So we copy this thing and do then rake convert. and we replace the generated procedure and compile it once again. And then we look into the assembly, and this is actually the right behavior because the index is now moved by 1, so the last element is 0. But if I write 4 and 5 here, then it should be 3 and 5 again. Yes, and just for testing we take also the third element and say it is 7, then it should be assigned to the 6th field. And it doesn't work because I'm missing an I here. Okay, and now we have 3, 5 and 7 as expected. The next thing to take care about is the type size. So the base type of an array isn't of course always 4 byte long. It can be an aggregate type like another record, and we have to take the actual size of the type to calculate the offset. We have the symbol table here. We do actually something similar for the field access expressions, and we will go here to the stage 18.2 and we look at the TSC designator is the correct place, and this is field access expression. And I also want to put this this code into a separate procedure because this procedure is getting a bit long. So we will define a TIC field access expression procedure. It will probably have almost the same arguments, I suppose. We actually do not need anything special here. And I want to move this code in there, except this field access expression variable. We do not need this, but we copy this stuff. Reduce the indentation. So, and the first argument will be field access expression and not array access expression. Then we need to copy some variables. So we need designator base, aggregate type, I think, field count, current field, actually almost all of them, field type I think as well. I think actually we need almost everything. So we can paste it here and see if we are missing something. The reference expression and field access expression. Oh, this one should be, of course, field access expression as well. Field access expression. The reference expression is probably isn't used. The reference expression isn't used here. So, and we actually want to return the first instruction at the end. Or of course is address, and his address can be different here depending on what it is. And I have already a procedure for this TC enumeration value for the enumerations. I probably can define a procedure just for the record field access. Yeah, let us remove this if else as well. So we still have a problem somewhere. By our problem is that the designator expression still requires the isAddress variable. So we define one and pass here the address of this variable. Designator field is already defined. We rename the label. Labels are used to define loops, because I have not implemented any loops like while or for yet. And this label should be actually used somewhere, I would think. Exactly, so we rename this one as well, field access expression. That compiles at least. And we can call here this procedure. So I don't know if I can just remove everything here. Yeah. Let's just remove this stuff and replace it by lnotic field access expression. The first argument will be field access expression, and then we actually have the same time operand type, operand value, and operand length. And we set the isAddress variable to 1. We can actually write false and true. Because field access is always addressable. It is always an L value. Okay. Let's put here 1 and 0 just to be sure. These variables are probably not set there. That could be the reason. No, I define them actually here, so I get this field access expression aggregate for the base type, and then type decoration as the type of the aggregate. And then I call this stuff here. This looks fine actually, but I think that I'm missing the symbol table here. So now it compiles. We can remove just a few variables here. I think field offset and current field, probably these 3 aren't used anymore. Aggregate type is used by, we do not really need this variable, because just to do the nil check we can use the whole expression here, so we do not need to set this one. And now we have aggregate base, designator base it is. So the designated base, we need it, yeah, we do need other variables, but this aggregate type can go. Then last instruction is used, first instruction is used, field type isn't used, I think. And the reference expression, field access expressions, expression both are used. So I suppose this is fine, and we can actually extract the reference expression into a separate procedure that wouldn't be run as well. The reference so the first argument would be this one, the expression itself. Then we need these three variables to save the target storage for the dereferenced expression, length, value, and type. And this should be actually enough. We can copy a few variables, probably these three. So these are local variables, and we can copy the code. So we move it in here. This isn't actually required. So if its address is 1, then last instruction and first instruction is, and when and then in the end we return the first instruction. And then we replace this code with this call then. So it will be then LNTAC, the reference expression, and we can pass the parser node directly because the type of the argument already have the correct type, so the parser node will be casted properly, and we need the is address variable passed by value. Do we need the symbol table? Yeah, probably to call the designator thing here. Okay, symbol table what? Oh, these are almost too many arguments. 3, 6. But 6 are still fine. But if we would have 8, it could be a problem, since they cannot be passed in registers, and I do not support passing the function parameters on the stack because it isn't implemented yet. So we need to switch these arguments, and this actually should be fine. And then we just set is address to true, and this one can go, and the variable can go as well. So we do not need is address. We are interested in the address of the not in the address, but whether it is already an address of this of the expression that is being dereferenced. So we do not need this one. We can just make it a variable, and then we can remove it from the call. And here we need to take the address of this variable, and this is actually it. This is a parameter, not a local variable. So we have first instruction here, LNTC designated reference expression pointer symbol table is address with 1D, of course. And that's it. Let us see if we can write here, for example, true now. Should actually work. Should actually work without any argument. But we let it as this because I do not want to break anything. So now we can write true here, and we can write false here, and true, and true, and false, and false. So, and now we made this function a bit smaller. Do I still need the last instruction here? No, I don't. But I need the designator base first instruction. Let us remove first instruction into result instruction, probably. Because we do not have instruction lists anymore, but just a single result. Well, probably here as well, and here, yeah, here I have result instructions and result instructions and result instructions, and here as well. And with this one won't be the last instruction, but the load instruction. So actually we wanted to look at how the offset is calculated with the correct type in the field access expression. It is here, and we read the type declaration from the type here. And the same thing we will do for the arrays. So it is the TAC pass. And I think also that we just define the same variable, aggregate type, and its type is also, this won't be ELNA type record, the aggregate type will be ELNA array, ELNA type array. I hope I have such thing. Yes, I do. So, and we need this designator base. Designator base is the expression that is indexed in this case it is ELNA3 expression, and actually it will be the same for arrays. So we define this designator base variable and say that that this has a type ELNA3 expression. and it is array access expression array. So this is the designator of an array, and its type is actually the same. So the designator will have the type set during the type check-in pass, and this is type decoration, and the aggregate type has then the size. So here we read length and members from the type information. Length, I think, is the number of the fields, and members is a pointer to a field array. So let us look at ELNA type record. It is defined here, so it has size, and size is the size we do not need the size of the array. This is actually, we need the size of this, or the designator base. But the designator base is not an, it is an ELNA type array, but it will have a base type. So this is actually fine. If we talk about a record, then it have a list of fields, and each field has some type. But in the case of an array, all elements have the same type, so we actually need to get this base, not this one, this base from the type, and it will be the base type, I think, and length is just the array length. So let us try to get the base. We actually can just override this aggregate type variable and say that its type is aggregate type base. Which is of course wrong, because aggregate type is ELNA type array, but the base type of an array is not an array, but it is some type. It is the element type. The type of the element type is just a pointer to the ELNA type, I think. So we say that this variable is element type, and now we actually have the size, and we can put the size in here, I think. No, please don't. This is this immediate value. So it is the value we multiply by, so we just say element type and size and see what happens. And it seems it compiles. And now we only have to test this once again. I would just go to the assembly and check whether the output has changed. So it was built valid stage 19 CLS 357. So at least this still works. We can go to the test code. No, I haven't generated the 19th stage. So before we can do it, we need to do rake convert, but the output will disappear then. Let us go to the boot stage 19 CLN. Then we copy this function again. Then we do rake convert. Reload the file and replace it with the previous version. And then we do build the compiler itself. And it still looks fine. So it is validation stage 19. And we have the same numbers. So the only thing that we still have to do is to test this with more complex types, so that the array type is not a single word but another aggregate. For that we go into the rake file and we define yet another record. With two fields, let us say. I need a different name for them. First and second. And we call it pair, and then we say that field 2 is an array of 2 pairs, and then we need to add a field into R2. Whatever, let us call it 2, 3, 4, 5, 6. And now we still need our function. It won't work probably because we cannot just assign field 2. But we copy it anyway and we call rake convert. And try to compile it as is. Oh. Yeah. So we can still get the size of R1. Let me go to the boot stage 19 CLL now to the top of the file, so that I can see the fields. So we allocated R1 and we want to take this record and to assign some values to the second field. It doesn't have the index 3 anymore because we have only 2 elements, but after indexing the element we can access a value inside the array, and it will be first and second, and in this case 1 2, and we can just copy this 2 and replace the index with 2, and let us say that this element is 7 and this one is 11. Then we assign this thing to R2. This is fine, and in R2 we still have all these fields, so it should be more or less fine. Yeah, probably the field access after the array doesn't work properly. It can be if I define a variable p of type pointer to pair and then allocate some memory for it, and then I set its fields first to 3 and p second to 5. And then I do memcpi where my target is R field 1, for example. No, the first element of the field 2. My source is the P and we copy 8 bytes. Oops. Where was the assembly? build valid stage 19, we have all the zeros, and we just copy the same stuff into field 2 too. Then we assign R to R2, and all the fields are still 0. My progress so far is that if I define a pair, so a type with 2 fields, and then if I create a record where one field is an array of pairs with 2 elements, and we have then R2 with the same memory layout, and then I allocate this R1 and assign just a value to a field. So field 2 is an array of pairs, but I assign an integer, which is not legal, but it works. And it works in the sense that the offset are properly calculated. So here is the output of the memory, and the first value is 3, the second 0, the third is 5, and then the last one is 0 as well. So what we can see here, that it calculates properly the offset to the second element. So we have 2 elements, each element is 8 bytes, the size of the pair type, and it assigns a value to the first element, and then assigns a value at memory 8 bytes from the beginning of the array. So the calculation of the array offset works as expected. But what doesn't work, I cannot specify a field here. So for example, first we have some problem here where we do not where I don't generate the correct code, but okay, at least the array offsets for the access of array elements works as expected, and I will leave it here for today, and we'll look why more complex expressions where the array access and field access is mixed, why they do not work properly, because I need some time for that.